I'm Dr. T, and welcome to my office. So today I got two questions for the Q&A. First question is, what's a glycoside bond? So glycoside bonds are going to be the connections between carbohydrate monomers. What you're going to have is you're going to be forming an acetal. So when you had your carbohydrate in its linear form, then at that point you would have had what we call the anomeric carbon. This is a carbon that has a carbonyl on it. And then that will have undergone a chemical reaction with one of the other alcohols, usually one about 5 carbons away or so. And that will then form a 6-membered ring, and that carbon will now become a part of, the anomeric carbon will become part of a hemiacetal, which is an alcohol, carbon, ether, all right in a row. This is then going to react with an alcohol on another carbohydrate. Typically, if you're thinking glucose, the anomeric carbon is carbon 1. It's going to be interacting with carbon 5 to form the ring, and then it's going to be interacting with carbon 4 of a different glucose to form the glycoside bond. And so this would be for like starch, glycogen, cellulose, those guys. Okay, so now you have what is effectively a carbon that has 2 ethers on it. One to one carbon that's part of its ring, and one to another that's part of another ring. Now, all of these guys are incredibly chiral, and when you form that original hemiacetal, so when you originally formed the ring, the carbon could go in one of a couple of configurations. Usually speaking, we draw them kind of like an up and down, where when we're drawing this, typically we're going to draw the number 6 carbon, which is not part of the ring for glucose. That's going to go up. If the anomeric carbon, that alcohol, is going opposite, that we call an alpha. Now, it's actually a slightly more complicated definition, but this is good enough. Alcohol going down, with, remember, the carbon 6 being the definition of which way is up. If the alcohol is going down, then when it forms a glycoside bond, that will be an alpha glycoside bond. If it's not attached to a glycoside bond, then that hemiacetal can break and reform, so it can sometimes be up, sometimes be down. It doesn't matter. So we don't really deal with that. We don't worry about that one. But once it forms the ring, if it formed the ring so it's down, that's the alpha configuration, and then it does a glycoside bond, we call that alpha. So it'd be an alpha 1,4 glycoside bond. If, on the other hand, it was in the up position, which in reality is the out. So down is well described as down, but up is actually out when you look at it in 3 dimensions and not in a stylized drawing. That's what we call beta. And so that would give you a beta 1,4 glycoside bond. In this case, the beta, because it's nice and linear, ends up being harder for enzymes to attack. You have to have a different set of enzymes. There's less of them out there. The alphas are easier for the enzymes to attack because it creates a bit of a kink, a little bit more room for the enzyme to get in there. Your energy storage are going to have alpha. Your structurals, for the most part, lactose is an exception. Whereas your structurals will have betas for the vast majority of the times. Okay, second question was, what is PCR? So PCR, polymerase chain reaction, is a way of effectively photocopying your nucleic acids. Typically we run it with DNA. It does work with RNA, though, as well, with some heavy modifications. So what you're going to do is you're going to take your source DNA. That goes into a test tube. You're going to have nucleotides, so remember that's the monomer, and these are going to be the triphosphate varieties, because in order to make these, you're going to have the triphosphate for the energy. And then you're going to have an enzyme, Taq polymerase. This comes from a high temperature loving, I believe it's an archaea, that doesn't get denatured at high temperatures, or, well, reasonably high temperatures. So this enzyme is going to copy your DNA for you. Now, it doesn't do it automatically. You have to give it a little bit of help. So once these are all in the tiny little test tube, and these are usually tiny little cute little plastic snap cap tubes, you heat the thing up, and you're going to heat it up enough that the DNA is going to split apart. It's going to have individual strands. So originally it was double-stranded, but it's now too hot. It's now 2 single strands. In this test tube that I forgot to mention earlier are a series of primers. DNA polymerases can't just start on the end. They have to start, a little bit down. So these primers have, a few nucleotides attached. They're going to bind to the DNA. Once they do, then the polymerase can hop on and then start copying it. So what you're going to end up doing, you heat it up so they split. You cool it down a little bit. That way the polymers or the primers can start to attach. And you're just going to cycle it up, down, up, down, up, down during the heating and cooling phases. Just taking them apart, then cooling it down so that the parts can combine and can be copied. Up, down, up, down, up, down. Every time you go through a thermal cycle, you double the amount of DNA. So obviously you're starting with quite possibly literally one strand. And after several hours worth of cycling the temperature up and down, you can be left with billions very, very easily. So it's a great way of detecting things. We use this in forensics. So you've got some blood, you need enough DNA to actually do anything with. Blood doesn't have a ton of DNA in it. So you can amplify the DNA that way. If you're looking for a specific genetic sequence, so if you're trying to figure out if the invasive Asian carp has infested the Great Lakes, then you take some pond water or lake water, try and do PCR with a primer that matches the invasive carp DNA. If you copy invasive carp DNA, you know you have a carp problem, which there's a carp problem. Alternatively, right now we've got the whole COVID-19 issue. And the current test does this. You do a primer that matches, in this case it's actually the RNA of the COVID-19. You cycle it through, and if you're able to get genetic material out of it, that patient has COVID-19. If you can't, then they probably don't. So yeah, those were the two videos that we have been going for. What am I talking about? Those are the two questions that I had in the question bank. So with that said, I'll see you next time.